We have seen how the stars are born from the interstellar matter. But what next? Here's a tip. Keep an HR diagram handy. I'm Shweta from Astronera and I welcome you to our course, The Star Stuff. We discussed in the last lecture how the classification of the stars on the HR diagram helps us understand the evolution of the stars. In this lecture, let's understand how the stars evolve. When a new star is born, it is placed at the bottom of the main sequence. It has less temperature and is also less luminous. The duration of its life on the main sequence depends on the amount of hydrogen available to be consumed in the core of that star. Also, the rate of hydrogen consumption matters here. The more massive the star is, the shorter is its main sequence lifetime. The small stars consume the hydrogen very slowly, hence they live longer on the main sequence. During a star's main sequence lifetime, it somewhat expands and the increase in its luminosity is modest. Core hydrogen fusion ceases when the hydrogen is exhausted in the core of the main sequence star. As the star gets old, this leaves the core with nearly pure helium surrounded by a shell through which hydrogen fusion works its way outward in the star. The core shrinks and becomes hotter, while the star's outer layer expands and cools. This is how the star on the main sequence becomes a red giant star. As the star becomes red giant, its evolutionary track moves rapidly from the main sequence to the red giant region of the HR diagram. The more massive the star, the more rapidly this evolution takes place. When the central temperature of the red giant reaches about 100 million kelvins, helium fusion begins in its core. The process is known as the triple alpha process. It converts helium to carbon and oxygen. In more massive red giants, helium fusion begins gradually. In less massive red giants, it begins suddenly. This process is known as helium flash. After the helium flash, the low mass star moves quickly from the red giant region to the left, roughly horizontally across the Hertzsprung-Russell diagram, and hence the stars in this phase are known as horizontal branch stars. Without nuclear reactions to maintain the core's internal pressure, the core again contracts until it is stopped by degenerating electron pressure. This contraction releases heat into the surrounding helium-rich gases. The new stage of helium fusion begins in a thin shell around the core. This process is called shell helium fusion. History now repeats itself. The star enters a second red giant phase. The outpouring of the energy from shell helium fusion causes the outer layers to expand again. The low mass star ascends into the red giant region of the HR diagram for a second time, but now with a greater luminosity than before. These stars in the second giant phase are known as AGB stars. Before this, the star loses its mass only gradually through steady stellar winds. But as it evolves during its AGB stage, a star evaporates its outer layers. The aging star undergoes serious bursts in luminosity, and in each burst, it ejects a shell of material into the space. Eventually, a small hot star remains at the center of the glowing ejected gas surrounding it. As this material expands into the space, dust grains condense out of the cooling gases. Radiation pressure from the star's hot, burnt out core acts on the pecks of dust, propelling them further outward. Now the core of the star is exposed, and with a surface temperature of about 100,000 kelvins, this exposed core emits ultraviolet radiations. These radiations are intense enough to excite the atoms in the ejected gas. These gases then glow. In the result, we get beautiful planetary nebula. We cannot observe the planetary nebulae which are older than 50,000 years. The shell is then spread out really far into the space and it simply fades away. The central star is called a white dwarf. Even though the star is pretty small, it's just of the size of the sun, its density is million times that of the water. If a teaspoon of the matter from the white dwarf was brought on Earth, it would weigh as much as a full-grown elephant. When a white dwarf stops generating energy via nuclear fusion, technically it's no longer a star. It's a stellar remnant. It's still hot, but not from the activity in its core. Think of the last stages of a white dwarf's life as more like the dying embers of fire. Over the time, it will cool and eventually get so cold that it will become a cold dead ember. A cold dead white dwarf is then called as a black dwarf. No known white dwarf has gotten this far yet. That's because it takes billions and billions of years for the process to occur. Since the universe is only about 14 billion years old, even the first white dwarfs haven't had enough time to completely cool down to become black dwarfs. This is the typical life of the star. However, the stars come in variety and hence they have different types of deaths as well. The planetary nebulae and the white dwarfs mark the fate of the low mass stars. But what about the high mass ones? Stick with me to the next lecture and know.